In this video then we'll try to pull it all together, see if we can do that and show you that it really is just a right triangle to solve for all the quantities we need. So let's start again. We've got with what we know, we've got for any component or any circuit or any system, and it could be any one of those three. There might be some amount of resistance, there might be some amount of inductance, there might be some amount of capacitance, and of course, very importantly, what frequency are you applying to this component or this circuit or this system? And out of this, we're going to try to answer the question then, what's the total impedance? And we also know that the voltage, of course, and the current that flows tell us the impedance. But we also know that the voltage and the current are not necessarily going to be in phase. They're not going to be happening at the exact same time. They can get knocked out of phase by the bucking or boosting, bucking and boosting, or the charging and discharging of a capacitance, or the bucking and boosting of an inductance. So you have to put all that together, and it all takes the shape of a right triangle, and that's what I want to show you, how it all fits neatly into right triangle math or trigonometry. So let's see if we can get there. So given these elements, plus maybe it all hinges on what frequency you're using too, where do we go from there? Like we said before in previous videos, R doesn't really change. It's not affected by frequency. L and C certainly get a certain amount of reactance based on the frequency and also their components. So from L, we can calculate how much inductive reactance is there based on the inductance, but not the inductance alone, also the frequency. And we can also get a certain amount of capacitance, capacitive reactance based on what capacitance is there and what frequency we're using. Remember, if you forget, that's 2 pi FL, and it's 1 over 2 pi FC. That's how we get our capacitive reactance, okay? So now we've gotten a certain amount of resistance that's going to impede current. This is going to also impede current. This is going to impede current. Not at the same time. They're also going to knock things around a little bit as far as phase goes. So we got to account for all that. But you're going to have a certain amount of each of those three. And of course, XL and XC cancel. But let's draw this. Okay, so you're going to have a certain amount of XL. You're going to have a certain amount of XC. You're going to have a certain amount of R. And we represent that with these these vectors, because that is the relationship they have to each other. From that, you get the net reactance, and if it's more inductive than capacitive overall, and again, it could be a component, it could be a circuit we're talking about, it could be a system, you'd be left with something like this, right? Certain amount of net inductive and a certain amount of resistance. But it could also wind up being true that your overall net reactance is capacitive, and then you would turn it into this, depending on how much inductive reactance, how much capacitive reactance. And that's where your right triangle forms then. Can you see that, let's take the overall, you're left with a net inductive. I guess I should put another one in here. If X and XL and XC are exactly the same, they'd cancel, and you could have just a simply purely resistive circuit. That's possible too. They can cancel each other out. If it's overall inductive reactance that wins. Let's show you that right triangle, right? It's sitting here. Let's say I have this and this. Well, let's translate this over. Okay. So there's my inductive reactance. And here is Z. That's the total impedance. Okay. So, and then this angle becomes important. So what we have then is a total resistance, a total resistance, total reactance. Total impedance is here to calculate using Pythagorean theorem, and we can get this angle using trig. This angle is actually the phase angle that will exist between voltage and current. And it's a positive angle, which means voltage will be ahead of current. And that makes sense because overall it's inductive reactance that's winning. Maybe we can redraw this right triangle to make it a little more obvious what we're dealing with. Okay. When you do shake it all out, you have a certain amount of reactance. You have a certain amount of resistance. Resistance is adjacent side, and reactance is the opposite side. And then you have a certain amount of impedance, and you have a certain phase angle that exists between voltage and current. So it is just a right triangle to solve for. Down here, if you have capacitive reactance that wins out, your angle is simply then a negative angle, which shows that here's your negative angle. It shows that voltage will lag current. Okay, so that's Z and theta. Okay, and all the information is contained in these values. Altogether, I guess you have, a certain amount of X and R. You also have a certain amount of total impedance and a phase angle between voltage and current. And they call X and R the rectangular components. Well, you can see that, I think, right? Let me see here. Let me highlight that. They kind of box in, right? So these are your values. But X and R are your rectangular values, or your component, your X and Y components of the vector Z. Z and theta are referred to as the polar coordinates. So we could put that here. You might run into that terminology. Rectangular, the sides of the rectangle. The rectangle contains all the information, and you can get the same information if I give you the two sides here. You already know this diagonal and this angle, right? It's right triangle stuff. These are, or I could give you the polar coordinates. The polar values tell you everything too. So if you know this length and this angle, draw it, and you know this, and you know this. So if you know, actually, if you know any two, you can get the other two. When it comes to our final sort of thing that we're going to arrive at is, if we get this, usually they come in pairs, like the rectangular ones you might know, and you solve for polar, or if you know the polar, you solve for rectangular. But, I mean, it's true if you know any two, you can get two. So let's just make a note of that, I guess. Yeah, if you know any two, we've seen this kind of thing before. Just to make a note for ourselves. That's easy enough to do. It comes down to here again. So what we're saying is if you know any of these two, if I know the total impedance and the resistance. I can solve for the phase, phase angle and the reactance and so on. So we'll show you how, but it's going to just use trig to get that done. Yeah, that's kind of what I want to kind of show. Maybe we can take this right triangle and we can say to ourselves, maybe we know, if we know the resistance and the reactance, we know we can get Z. We can get that. We'll better show you that. We haven't showed that. That's a new thing. We know the total impedance that comes from this resistance and this much reactance. It's just Pythagorean theorem. We can do that, right? A squared plus B squared equals C squared. So what is that? X. Oops, let me get out of that. So what that means for us is, x squared plus r squared equals z squared. That's a little bit of right triangle stuff. And what that means, of course, is to solve for z, you can just rearrange all that. If you want total impedance from reactance and resistance, we did this in a previous video. Whatever your net reactance is, you square it and add it to whatever your total resistance is. You square that, square it, and square root it. Got your total impedance. That phase angle that's going to exist between voltage and current is easy enough to get with maybe the tangent function. If you're looking at a certain amount of reactance that sits in your component or your circuit or your system, here it is, and here's my resistance. So we can use those rectangular coordinates or rectangular values to get the tangent, to get the angle, because it's the tangent of the angle that is opposite over adjacent, right? And so here's the opposite side of the angle, here's the adjacent side of the angle. So tangent equals, for us, its opposite is x, reactance over r, right? So do you want to know what angle will exist given a certain amount of resistance and reactance that exists in your component or your circuit or your phase? I keep saying component or circuit or system because you can solve for any one of those. You can zero in on just the voltage across a single component versus the current going through it. Or you can zero in on the circuit voltage as a whole versus the circuit current as a whole. Or you could zero in on the system voltage, as a whole versus the system current. So to get the characteristics then of that component or of that circuit or of that system. All right, so the angle that we're looking for here then is easily solved. Remember, when you do algebra with trig functions, the tangent of the angle has this ratio. But if you know the ratio and you want it to rat out the angle that's responsible for this ratio, take the arctangent of the ratio. So I want to solve for the angle, so I need to get the arctangent or the inverse tangent, however you want to call it, x over r. That'll do it. And that's going to be another function on your calculator. So you take the ratio of reactance to resistance, and take the inverse tangent of that ratio. It'll pop out the angle that's responsible for that ratio. And that angle is the phase angle that will exist between voltage and current, because they get knocked out of phase by the bucking, boosting, or charging, discharging. They're not necessarily in phase. They can be in phase if I don't have any reactance, for example. The inverse tangent of 0 is 0. So there won't be any phase angle between voltage and current if there's no reactance. I think that makes sense to you, right? Okay. So this would be some, some trig, some right angle, or some right triangle math. Maybe if based on solving for the polar values of what's the total impedance, what's the phase angle between voltage and current, based on how much reactance I have and how much resistance I have. Now we can go the other direction too. Maybe let's look at the other trig relationships that we know of. There's some other trig functions that are pretty common, right? Cosine, let's see, sine of the angle. For that's what's that? The opposite over the hypotenuse. So for us, that's x over z. That's a ratio that we can use. Cosine's adjacent over hypotenuse, right? So that's r over z for us. And look what shakes out of these relationships. Maybe I know the angle. I can measure with my scope the angle that exists between the voltage and the current. And I can also look at what is the voltage that's being applied and what is the current that's flowing and get Z, you know. So I might know the polar ones and I can say to myself, whatever angle I see between voltage and current, I can take the sine of that, and whatever the actual impedance is, I could just use Ohm's law. I could say voltage divided by current and get Z, and the angle between voltage and current, and get the sine of that. And guess what? And this is going to pop out the value of reactance that exists, right? Because I just did, and you're looking over here, I just brought Z over to this side. But at the bench, that's something you might do. You can look on your scope and see the angle that exists between voltage and current. And that same voltage and current you can do Ohm's law with and get Z. And bam, you know how much reactance there is in that component or circuit or system. Of course, we can do the algebra for this, and you could use the cosine of the angle that exists between voltage and current times the total impedance that you could get from Ohm's law, and out pops the amount of resistance that is in this component or circuit or system, depending what you're looking at. If you're looking at a component voltage, you're characterizing the component. If you're looking at the circuit voltage, you're characterizing the circuit. Okay. So I hope you can see that it all comes just from right triangle stuff. It's not too crazy if you keep it sort of in that organization, right? This all is just a simple right triangle. It's how everything relates, even though it seems to kind of be a lot to contain, or a lot to grapple with. The right triangle will be our friend here. It really helps us keep ourselves organized as to what's happening. This is the relationship right here between resistance and reactance and total impedance and the phase angle that could exist between voltage and current given a certain amount of reactance. I think you can see if you don't have any reactance, you won't have any angle between voltage and current, right? Conversely, if you don't have any resistance, look what happens. If resistance shrinks all the way back to 0, you have 90 degrees of a phase angle between voltage and current. You might have voltage leading current, in which case you'd have positive 90 degrees. If you have no resistance and it's purely inductive reactive, pure inductive reactance will always pull a 90-degree angle between voltage and current. And purely capacitive, if you look down here, I guess, resistance could go all the way to 0. And if you have a purely capacitive component or circuit or system, there'll be a 90-degree phase angle between voltage and current. And we kind of knew that because that's how capacitors behave, right? You get current first and then voltage follows. And for inductors, it's the opposite. You get voltage first and then current follows. But so this right triangle, I hope, becomes like your best friend and really keeps it all organized for us, I think. See if there's anything else to add. That might be it. But that brings in the phase angle for us between voltage and current. Maybe that's a wrap. So, right. When we're working in the AC course, it's always just those four things. And those four things relate to each other in a right triangle. Okay.